Wow, I know there has been a ton in this chapter. We've really gotten to some weeds on some things, but hopefully you've also seen sort of the big 30,000 foot view. One of the big things that's important from this learning unit is understanding how high versus low blood sugar situations are going to drastically change the kinds of metabolic processes that we have happening in our bodies. So we've learned about glycolysis, gluconeogenesis, glycogenolysis, so kind of those top down and bottom up approaches for remedying low blood sugar levels. But one last piece here, one last little detail that I want to sort of talk about is how we can regulate those two critical enzymes that we see for glycolysis and gluconeogenesis, right? So PFK is the rate controlling step for glycolysis, and then FBPase is the rate controlling enzyme for gluconeogenesis. So we learned already in our glycolysis learning unit about some of the structural details for PFK and how we can modulate R state versus T state. Remember, that's where we would have that helical unwinding that changed whether there was a negatively or positively charged amino acid in the enzyme active site that determined whether or not we had productive binding of F6P or not. If that's not clear to you, make sure to go back and rewatch that video kind of on PFK structural kind of details. But the key here is that we can control the activity of enzymes like PFK and FPBase through that allosteric regulation, R state versus T state, changing shape, right? And we learned with PFK how that modulates what we have in the enzyme active site. But what we're going to do right now is learn about an important molecule that helps both of those enzymes, PFK and FPBase, kind of control their R state versus T state. So they are allosteric regulators, okay? Or this molecule, F26P, is an allosteric regulator. So just like we have to remember and get into our brain that insulin is a fed state signal and it's, high blood sugar, and glucagon is a low blood sugar, need state signal, I need you to get into your brain that F26P is a fed state signal. So say it a couple of times, you get it in your brain. F26P is a fed state signal. F26P is a fed state signal. F26P, a fed state signal. Now, the other thing that we have to make sure we get into our brain is the understanding that glycolysis is actually a fed state pathway. And that can get a little bit weird to think about because you're like, wait a minute, Dr. Perenni, like we talked about how when you're in an anaerobic state and you need ATP quickly, you can use glycolysis to make ATP. Absolutely. But the way to remember this is knowing that glycolysis is fed state. That must mean its counterpart, gluconeogenesis, must be need state. And there's no way that we'd say gluconeogenesis is a fed state pathway. So remembering that gluconeogenesis is need state is that reminder to us that glycolysis is a fed state pathway. Okay, so F26P is a fed state signal and glycolysis is a fed state pathway. So all of this together must mean, and this is true, that F26P activates PFK and activates glycolysis. Okay, so, and we'll get into this in a slide in a couple of minutes here, but highlighting that, well, why would glycolysis be a fed state pathway? Okay, remember, if you've got excess glucose, that is very cytotoxic. That's very inflammatory. You need to get those blood sugar levels down. So there's lots of things your body's going to try to do to get that blood sugar into your cells, right? To get it out of your bloodstream where it's so pro-inflammatory. But then once you get it into your cells, you have to do something with it. So if you are not in a need state, that high blood sugar needs to be kind of dealt with. And when we make it into pyruvate by going through glycolysis and then taking it through pyruvate dehydrogenase chemistry to make acetyl-CoA, now, once we have excess acetyl-CoA, your liver is very effective at synthesizing that into fatty acids, assembling them into triglycerides, and allowing you to then store that excess glucose in your adipocytes, which we don't have limited reserves of. Okay, so that hopefully was my 30,000 foot view of sort of what's going on. We're going to get a little bit into the weeds here with understanding how F26P regulates both PFK and FPBase, ultimately regulating that substrate cycle between glycolysis and gluconeogenesis. Okay, So a little bit of details here on F26P. The first thing I want to highlight is the difference that we see when we take fructose 6-phosphate and make it into fructose 1,6-bisphosphate. So this is sort of the normal chemistry that happens in glycolysis and gluconeogenesis, right? So F6P making fructose 1,6-bisphosphate by PFK. That's what happens in glycolysis. Again, this is going to be active when we are in a D-phosphate state, sort of that fed state. Okay, and then fructose 1,6-bisphosphate can lose that phosphate. We can have a phosphatase, FBPase, right? Remove that decoration. Let's remind ourselves, we typically just say PFK and then FBPase, right, to regenerate F6P. That again, that is happening in gluconeogenesis, so that's going to be sort of need state. So that is going to be active when we've added that phosphate, when we are in a phospho sort of system. So this is stuff we've already learned about, highlighting right now that these are two separate enzymes. PFK and FPBase are two separate enzymes, okay? I want to transition now to think about, we also can take F6P and have a different enzyme kind of add a phosphate at the 2 position. So let me zoom in down here. This gets a little bit small down here. So here again is F6P. Okay, rather than adding a phosphate on the 1 position, like we did, there's no structures that are shown up there, but rather than adding it on the 1 position, we're actually going to add it on the 2 position. So not surprisingly, we need to have another enzyme that does that. And lo and behold, this is a really unique enzyme because it's another one of these enzymes that we call bifunctional. The first time we learned about a bifunctional enzyme was when we learned about glycogen breakdown, and we learned about that debranching enzyme that had the ability to move branches and also snip off nubs. Okay, so we're going to liken this to thinking about a 2-in-1 store, if you will. It's an enzyme that has 2 different stores that can do 2 different chemistries. Now, it's important to note both of these stores are not open at the same time, okay? So here, if we've got F6P and we're going to have a PFK2, so this is doing the same chemistry, phosphofructokinase, but we're adding it to the 2 position. So that's why it's called PFK2. Okay, we're going to be adding that phosphate here. So not surprisingly, kinase adds it, and then we're going to have an FBPase to remove it. These are 2 different activities on the same enzyme. So it's like a 2-in-1 store, highlighting we're never going to have both of those stores open at the same time because it doesn't make sense for one of them to be doing the decorating, the other one to do the undecorating, right? So only one is operational at the same time. This is another one of those weird situations where when we learn about how and why this enzyme is active, it's a little bit backwards, okay? This is a kinase doing chemistry, right? Kinase that's operational when it's in its D-phospho state. But the logic is still there. Follow with me for a second. Remember, F26P is a fed state signal. It's going to upregulate glycolysis. All of that we'd expect to be happening in a D-phospho system. So that's all consistent. But we just happen to need a kinase to make the molecule that is our fed state signal. So that's where a little bit of the disconnect comes in. So not surprising, it's consistent with what we'd expect. When we need to put ourselves in a need state, we're going to be having a phosphoenzyme, so one that's active when it's phosphorylated. So again, this multifunctional enzyme is either going to be with or without a phosphate. When it is without a phosphate and in its D-phospho system, it's going to be making F26P, and that F26P, fed state signal, activating PFK, activating glycolysis. Okay? When it's in its phospho state, it's actually going to be activating its phosphatase activity. So it's going to be taking F26P and making it back into F6P. And we're going to talk about on the next slide, when we have F26P levels fall, that means we're going to be upregulating gluconeogenesis, not glycolysis. Okay? So highlighting again, when that kinase activity is active, it's going to be active in a D-phospho state for that bifunctional enzyme. That's going to be increasing concentrations of F26P, upregulating glycolysis. Okay, take FPBase2, okay, that's going to be active. That phosphatase is going to be active when that store is phosphorylated. And again, we're snipping off phosphates then, so we're going to be decreasing the concentration of F26P, and then we're going to be upregulating gluconeogenesis. Wow, a lot there, I know. So let's put this all together on one of these sheets again. I hope you don't hate these. I know they're complicated and involved, but hopefully they're a way that takes all of this information and sort of puts it in a logical way for you to understand it. So let's think about sort of what's happening here. Just like we've had when we've seen sheets like this before, we're going to talk about the centerpiece first. So again, we're talking about what is the molecule gland enzyme that we're talking about. So we're first going to ask what's happening with the pancreas, what state are we in, what's the pancreas secreting? What is that doing to cyclic AMP levels? Remembering that cyclic AMP levels are a direct reflection of what kind of chemistry is happening with adenylate cyclase. And then we're going to be asking the question, what is happening with this bifunctional enzyme, that PFK2 FPBase2? So kinase and phosphatase activities within the same enzyme. Remembering they're not operational at the same time. Only one store is open at a time, but we're going to ask which store is open, and so what is it doing, okay? And ultimately, what that store is doing is going to determine what the concentration is of F26P, remembering that F26P is a fed state signal. And then we're going to ask the question, what is happening with PFK and FPBase? Again, noting that even though these are two different enzymes, they are never going to be both active at the same time because we are not going to be actively doing glycolysis and gluconeogenesis at the same time. And always with these charts, we want to be coupling sort of a signal with a net outcome. What are we doing with that signal? Okay, how are we remedying that situation? All right, so let's talk first over on the right here with what happens with low blood sugar levels, okay? Low blood sugar levels means the pancreas is going to be secreting glucagon, okay? And that's because we are in a need state, right? And I'm going to kind of highlight and put on top here. Need state, we think about as phospho, right? Okay, so adenylate cyclase then is going to be active, okay? So we're going to use, again, this formalism that we've seen before. This means we're going to be activating adenylate cyclase. So an arrow means activating. That means we are going to be increasing the concentration of cyclic AMP. And importantly, that means we are going to be activating pKa. And I didn't have pKa on here, but remember, pKa is one of those master phosphorylators, okay? So when we are phosphorylating this bifunctional enzyme, okay, when we're phosphorylating it, that means that we're going to have the FPBase be active. So in this situation, this means that the FPBase is going to be what's active. Let me grab my colors here to indicate that this is going to be active. All right, so the FPBase is active, okay? So what is the chemistry that's happening then? Okay, we're going to be taking F26P, and we're going to be snipping off that phosphate. So this enzyme is going to be snipping off that phosphate, and we're going to be making F6P. So at the end of the day, what this means is we are decreasing the concentrations of F26P. Should have had a comma in there, F26P. Okay, so we are decreasing the concentrations of our fed state signal. Okay, so what does that mean in terms of what's happening with PFK and FPBase? Again, let's use our formalism for how we think about things here. We are going to be inhibiting PFK and activating FBPase. Well, we need to remember that inhibiting PFK and activating FPBase means we are increasing gluconeogenesis. Right, and this is important because we started out saying we are in low blood sugar, we are in a need state. Okay, so this is, again, our bottom-up approach to remedying low blood sugar. Okay, let's go over to the flip side here and talk about what's happening when we have high blood sugar. And again, we're going to be in that D-phospho state. All right, so we are going to have increased concentrations of insulin from your pancreas, and that's because we are in a fed state. So in this case, we are going to be inhibiting adenylate cyclase. Our concentrations of cyclic AMP are going to fall, and we are going to be inhibiting pKa. Okay, we're probably going around, and I didn't put this on the other guy over here, but we probably can say that we are activating FPP1, right? That phosphoprotein phosphatase 1. That's one of our master dephosphorylators, okay? But in terms of this sort of bifunctional enzyme, okay, the activity that's going to be active now is going to be the PFK activity. So PFK2 is going to be active. And let me just fix this over here. I should have put, just so that we don't get confused when we're talking about things, this is FPBase 2, right? So PFK2 is going to be active, right? And that's a little bit odd, right? It's a kinase that's active under a D-phospho system, okay? But let's remember what this kinase is doing. It's taking F6P, and this enzyme is going to be converting F6P into F2-6P. So that means we are increasing the concentration of F2-6P. So we are increasing the concentration of that fed state signal. Okay, so let's talk about now what that allosteric regulator does for those two different enzymes, PFK, rate determining enzyme in glycolysis, FPBase, rate determining step in gluconeogenesis. So now we are going to be activating PFK. Could not write there for a second. Let me fix this here. I'm going to activate PFK. We are going to be inhibiting FBPase. Okay, so activating PFK means we are going to be activating glycolysis. Okay, and so we mentioned this on our 30,000 foot view, but let's kind of put it in here. I'm probably going to run out of room, so I'm going to have a couple of arrows here. But we're going to increase glycolysis in a fed state situation, because in a fed state situation, we've got excess glucose. And if I haven't convinced you enough, high levels of blood sugar is hugely problematic. It's very inflammatory. It's very damaging to multi-organ systems. So you really don't want to have high blood sugar for long periods of time. Okay, so let's talk about what happens then. Excess glucose, if we're upregulating glycolysis, is going to be made into pyruvate. That pyruvate, by pyruvate dehydrogenase chemistry, is going to be made into acetyl-CoA. Okay, that acetyl-CoA then can be made into fatty acids. Those fatty acids can be assembled into triglycerides, and then those triglycerides can be stored in our adipocytes, our fat cells. And that is an unlimited reserve. For better or for worse, we've got limited reserves of our glycogen stores in our muscle and our liver. So once those are tapped out, if you still have high blood sugar levels, you need to put that glucose somewhere, and you're going to store it in your adipocytes, because those really don't have, we just can make each adipocyte bigger, or we can allow them to divide and then create more of them. Both ways that we can increase the capacity of fat stores in a relatively unlimited sense. Wow, I know that was a lot. This was the last kind of concept here to think about with our learning unit on glycogen metabolism and gluconeogenesis. But another one of these important molecules that serves to regulate two really important halves of an important substrate cycle to maintain glucose homeostasis.